Hello everyone, and thanks for tuning in to another intensive physics virtual lesson. We're going to continue our studies in Chapter 7, which is generally on universal gravitation. Last class, we talked about this thing, gravitational force. Okay, and so basically what we said was objects that have mass are attracted to each other. Okay, and so we can see here we've got two spheres, they have some sort of mass, and we can see that there's a force on those objects. Isaac Newton was the one who developed this theory, and he actually developed the equation for universal gravitation. He said as long as we account for the magnitude of each mass, and r, which is the distance between their centers, we can actually determine the force of gravity on these objects. Now last class, I said we were going to be able to apply what we learned on the force of gravity to an object's orbit, or objects in space. The revolutions of the planets. But in this case, we're going to talk more specifically about satellites and how they revolve around the Earth. Satellites are very important to us. They help provide us with cell phone coverage, internet, even your GPS signal uses satellites every day. So making sure that they're not crashing into the Earth or flying into the space is very important. So satellites follow these pathways and they're called orbits. Okay, you can see they're kind of outlined in this white line here. Apologies if you kind of can't see that. But the shape and the size of these orbits are dependent on a couple factors. In order for me to explain to you how orbits work, I'm going to start off with a pretty basic example. I have a cannon on top of this grassy hill. And I'm going to go ahead and fire a cannonball out of it. We know that here on Earth, if we did this, the cannonball would follow a trajectory that would eventually land it somewhere on the ground, and the cannonball would stop. But let's say, for an example, we fire the cannonball on an Earth with no gravity, and we look at the trajectory and it kind of just goes straight. Based on our previous studies on mechanics, we would say, hey, this kind of makes sense. Remember Newton's first law of motion. An object in motion is going to stay in motion unless it's acted on by an outside force. Okay, so in this case, the cannonball, once it is shot out of the cannon, was to continue at that same velocity and direction forever and ever and ever. What brings it down to Earth is gravity. So now that we understand how this example works, let's kick it up a notch and take a look at it from the outer space. Let's take a look at the Earth. I'm only kidding. Let's take a look at the actual Earth. We're up in space, and we have a cannon mounted somewhere on the Earth's surface. We're going to go ahead and fire that cannonball again. Now, if we pretend that there's no gravity, what's going to happen to that cannonball? It's going to keep going straight at that same velocity somewhere out into space. But if we think of gravity and we include it in our example, we notice that it's going to kind of follow that same trajectory as on the grassy hill. Now, if I add lots of powder to this cannon, and we really gear it up, and we fire that cannonball nice and hard, we're actually going to find that the cannonball is going to make a complete revolution around the Earth. Now, if we fire it at the correct velocity, the cannonball's path will get no closer nor further away from the Earth. Moving the cannonball at too high of a velocity means that it's going to fly off somewhere into space. Too low a velocity, it's going to crash into the Earth. So we have to find that sweet spot. We're able to find this using an equation that comes right out of our book. We know that the velocity necessary for that object, in this case it's a satellite, is going to be equal to the root of our gravitational constant times the mass of the Earth, all divided by r, which again is just the distance in between the two objects. The mass of the Earth, and make sure you take note of this, is equal to 5.97 times 10 to the 24 kilograms. Remember that g is going to be equal to 6.67 times 10 to the negative 11. And remember, like I said before, r actually kind of stands for the radius of the orbit. It's just the distance from center to center between these two objects. So let's take a look at an example problem here based on what we've learned today. The speed of an object orbiting, what is the speed of an object orbiting above the Earth 50 million meters? Okay, so above Earth's center, 50 million meters. What is the speed of that object orbiting Earth? I'm going to go ahead and start this problem by writing down the equation we just learned. Okay, now what I'm going to do is I'm going to take a look at the question and see if there's any information that I can pull out that would be relevant. So we've got this number right here. It's going to be 50 million meters above Earth's center, or away, I guess, away from Earth's center. Okay, and so we remember that that's r, 50 million meters. Okay? The other two variables in this equation is g, which I can remember is 6.67 times 10 to the negative 11, and then the mass of the Earth, which is going to be 5.97 times 10 to the 24 kilograms. There's a familiar unit. Oh, what's the other thing I'm missing? I'm searching for v, okay, the velocity or the speed of the object that's moving through space. Okay, I think I have enough filled out to start solving, so I'm going to go ahead and substitute my knowns into this equation. Remember to include your units while we're substituting in our equation for extra points. And if we work out the math, don't forget the square root. We get a velocity of 2,822 meters per second. Don't forget those units and to box up that answer. 2,822 meters per second. A little faster than what we're used to with our kinematics problems. Well, thanks guys for tuning in. Feel free to put your questions in the Google Doc. We'll see you next class.